All right, moving on, our next video, we're going to look at vertical translations of the absolute value function. And the question, how does adding a constant to the output affect the graph of f of x equals absolute value of x? So I have a quick little visual I'm going to show you, and then we'll come back to this conversation right here. All right, so I thought this was a good visual to show you guys quickly what happens to the graph of our function, of our absolute value graph, as we change the function right here. So we see g of x equals the absolute value of x. I have a little slide bar down here. So I'm going to take this and I'm going to move it to the right. And if you look at the function, I'm going to go all the way up to here. What it did is it took the function, it's still the absolute value of x, but now it has a plus 2. And I moved it. So what happened? If I have a plus 2 on the end, can you tell what happens? Well, what if I move it some more and I go to a plus, let's say 4? So that's where the graph is. You can see this is where the original was. This is our parent function, just the absolute value of x. But I'm just changing. I can go all the way up to a 5. What if we subtract a number on the end? If I go minus 1 on the end, do you see what that's doing to our graph? If I go minus 2, or minus 2.5, or whatever the case may be, minus 5. So what you can see visually is any number that you add or subtract on the end here outside of our absolute value is vertically shifting our graph. It's going to move it up or move it down depending on if we're adding a number or subtracting a number. Okay, so we just saw as you add a constant on to your function outside of your absolute value bars, that is going to be a vertical translation. It's going to move it up and down. If you take a look at a couple examples here, we can see our parent function. The function is absolute value of x minus 4, so it got shifted down 4. That did change the vertex. The vertex, instead of being at 0, 0, is now at 0, negative 4. Over here, we took our parent function, f of x equals absolute value of x, and we added 2 to the outside. What that does is that is adding a constant. It changes the value of f of x. It changes our output when we add it outside of our absolute value bars, and that took our parent function and shifted it up 2 units, which did change the vertex. The vertex is now at 0, 2. These graphs both have an axis of symmetry. The symmetry line is going to be vertical, going right through the vertex, splitting your graph in half. And for both of those graphs, because all we did was shift up or down, that axis of symmetry is still at 0. So can we, for other functions, identify the vertex and the absolute 0? Or the axis of symmetry. All right. So p of x equals absolute value of x plus 3. So here's our absolute value of x. We can see that we're adding a constant onto the end. By the way, this is what we would call our k value. We talked before about a value being the number in front of the absolute value, so this is a k value on the end. That plus 3 is going to translate your graph up 3 units. What that's going to do to your vertex. So when I identify a vertex, I'll put a V and then my ordered pair. So that's all that V means, is that's my vertex. It was at 0, 0. If it went up 3 units, now it's at a 0, 3. And then because all it did was shift vertically, the axis of symmetry did not change. So the axis of symmetry is still x equals 0. All right, next example, we have g of x equals the absolute value of x minus 2. So that's our k value. We're adding a constant to the output of our function. That is going to translate the graph down 2 units. If we go from the origin with our vertex down 2 units, our new vertex is at 0, negative 2. And again, because we didn't do any shifting horizontally, the axis of symmetry is still at x equals 0.